In this video, you're going to learn about all the basics of static electricity, charging methods, and many variations of Coulomb's law so you understand it in one dimension, in two dimensions, and with a couple particles, and also with three particles as well. First of all, to understand the basics of static electricity, you want to take a look at the atom. In our picture here, we have some negative charges are electrons that are orbiting the nucleus, and in the middle here we have the yellow particles, which are protons, and the orange ones, which are neutrons. The only one we care about are the electrons. Just like it says here, electrons are the outermost particle. They're the only particle that's transferred. Now that's the way that everything gets charged up, whether it's your hair sticking up or a cloud getting charged up that's about to strike lightning. In all those cases, there's an imbalance of electrons, meaning it either gained electrons and became negative or lost electrons and became positive. So let's go ahead and make a note of that. So again, since our protons and neutrons are locked up in the nucleus, those aren't actually transferring. If they were to move anywhere, that means some actual mass would be moving from one place to another, but electrons can be moved from one place to another. If something were to become negatively charged, that would mean it would gain electrons. If something were to become positively charged, that means it lost electrons and has more protons than it does electrons. Now we got that out of the way, we have three main charging methods. The first one is friction, also known as the triboelectric effect. Now, if you have two things that are significantly different on the triboelectric series, they will charge if you rub them together. Most things, if you rub them together, will not get charged. Basically meaning that one thing holds onto its electrons very tightly and one thing does not. Okay, in this case, our balloon does hold on to electrons very tightly and our sweater does not. Now, let's say that both of these are neutral. I'm going to go ahead and draw some positives and negatives on them. This one, I can't really see it, so positives and negatives on there. There we go. All right, so first of all, they start neutral, which means that there's basically about the same amount of protons and electrons on each of them, and those positives and negatives would cancel each other out, and it would have a net charge of 0. Now, when you put energy into it and you rub the balloon on the sweater, when you have two things that are significantly different in their ability to hold on to electrons, then some electrons get transferred. Now what happens is, since the sweater is not very good at holding on to electrons, when that friction of the balloon being rubbed back and forth is applied to the sweater, then we have some movement of charges. We have the electrons going from here to here. And a lot of times I'll put electrons as a little e with a negative sign or just a bunch of negative signs. I would say, generally speaking, softer materials do not hold on to their electrons very tightly, so they can be pulled off. In things like a balloon that are very insulated, rubbery type materials, those ones do hang on to their electrons very tightly and charges do not flow through them easily. All right, so first you have some friction between the two, and then the electrons get moved to the balloon. Now the balloon has gained electrons, and then the sweater, here's my sweater right here, this little box, has lost electrons. So this one has a net positive charge. Not saying that it doesn't have any electrons, but there's just an imbalance. It has more protons than it does electrons. And now the balloon has gained electrons. It has a net negative charge. Same thing with this one. Not that it's 100% electrons, which it can't be anyways. It just has more positives, or excuse me, more negatives than positives. And then if you wanted to put a value with them, I won't put an exact value, but we'll say it would be something like, -5 microcoulombs, and this one would be +5 microcoulombs, meaning that whichever negative charge one gains is the same as the positive charge that other one has due to its loss of electrons. All right, that's friction and the triboelectric effect. Moving on to conduction. Conduction is typically talking about where there's some contact. Okay, now sometimes if something is pretty charged up, it can move close, and it doesn't necessarily have to touch it, but it's a similar idea where if something is pretty charged up, say for example we have a rod here that has an excess of electrons, it's overall negatively charged, and then we have something that's pretty neutral. So what's going to happen when they touch, because charges want to reach equilibrium, they are going to spread themselves out. So like charges repel each other, so negatives repel other negatives and positives repel other positives. But the negatives are actually able to move. So once you have a little contact here, you're basically sharing two surfaces, and the electrons are going to spread themselves out, and some of them are going to jump into this, we'll say, metal sphere. Now overall, your metal ball is going to have a net negative charge because it was balanced and now it gained some electrons. There's some imbalance of charge, so it is negatively charged. Okay, our rod technically is probably going to have a bit of negative charge too. It's going to be moving a little bit closer to being neutral after it has shared some charges and kind of zapped some electrons over to our metal sphere. All right, lastly, we have induction. So induction would be if you say you have that same balloon that snatched up a bunch of negatives from that sweater. It still has a net negative charge because it has more electrons than protons. What it's going to do is it's going to take two neutral objects, but it's going to shift their charges. So overall, say for example we have two metal spheres here. They're neutral, which means that they have the same amount of protons and electrons overall between the two metal spheres. But because it's near something that's negative, opposites attract, so it's going to be attracted to the positives, but more importantly it's going to repel the negatives. But negatives are the only ones that can actually move. So what it's going to do is it's going to take some of this gray metal ball's electrons, and it's going to cause them to shift over, and we call that polarization. Okay, and polarization is basically the shifting of charges when it's influenced by a charged object. So that's the same way a balloon sticks to a wall. When it's next to a wall, it pushes the electrons sort of deeper into the wall, and then the front of the wall looks more positive, and then it's going to attract to those positives. So in this case, what you do is you put the balloon close to these spheres. It's going to push the electrons back, and it's going to make this one more positive and this one more negative. Together, they're still neutral. But what you do is once you separate them, if you pull them apart, then the one on the left had lost some electrons, so its net charge is positive, and then the one that got electrons pushed into it, its net charge is going to be negative, and then you end up with two charged objects that were once neutral when they were kind of touching each other and sharing their surfaces. All right, there's our three main charging methods there. Biggest takeaway is number one, electrons are the only things that actually go from one place to another, and they go from one place to another in three different popular ways, such as friction, conduction, and induction. All right, let's get to some numerical stuff and take a look at some quantization of charge and some Coulomb's law problems. All right, our first formula is a pretty simple one. We have Q, which is the charge. This is going to be the net charge or overall charge. We have N, the number of electrons, and then we have E, the charge of an electron, negative 1.6 times 10 to the negative 19th coulombs. And then our charge is going to be in coulombs as well, and then N does not have a unit. So basically there, all you really do is, I'm not going to show any sample calculations, but if you had 80 million electrons, you just do 80 million times negative 1.6 times 10 to the negative 19th, and then you would figure out the net charge based on how many extra electrons it has. If it had lost charges, say for example it lost 10,000 electrons, your N value would be negative 10,000. And then once you'd multiply negative 10,000 by negative 1.6 times 10 to the negative 19th coulombs, you would get a positive Q value charge. All right, so let's go ahead and move on. Our main formula we want to take a look at is Coulomb's law, which is F equals KQ1 Q2 over R squared. Sometimes the R squared is written as D squared because that is the separation distance. Which is in meters. We have a constant over here that's always 9 times 10 to the 9th. And then Q1 and Q2 as in your charge 1 and charge 2, because obviously it would take two things to attract or repel one another. And then this is the electrostatic force of repulsion or attraction in newtons. All right, now if you're using this formula, this is what it's going to look like. So we're going to work out a few different problems. We'll start off with a simple one and get into slightly more complex ones. All right, so let's say we have one negative charge and one positive charge. We know that opposites attract, so this one is going to get pulled towards the positive is going to get pulled towards the negative. If we want to quantify that, we need a separation distance and we need some charges. This one we'll call it 1 microcoulomb. This one we'll call it negative 2 microcoulombs. Micro meaning times 10 to the negative 6th. So if we were to plug those in and we wanted the force of attraction between these two, we'll call it Fe for the electrostatic force. We're going to put in our constant, 9 times 10 to the 9. The way I like to type it in into the calculator is I like to type it in hitting 9, the double E button, and then 9 again. And then in your calculator, that will pop up as 9E9. And that's the same thing as 9 times 10 to the 9th. So that's my preference in plugging into the calculator. It kind of condenses things just a little bit. And our Q1, negative 2 times 10 to the negative 6th. And 1 times 10 to the negative 6th. Both of those all over our separation distance, and remember that's an inverse square relationship, so we're going to have to square it on the bottom. So what I typically do is I like to multiply everything in my numerator, press enter, and then divide it by the denominator squared. You can put everything in your calculator all at once. If you do, then I would recommend wrapping the whole numerator in parentheses to make sure your calculator knows that that's the whole numerator, the product of those three numbers. When you do that, we get an answer of negative 0.8 newtons. Okay, a lot of times, honestly, the sign isn't that important. I sometimes don't even really include the negative or the positive. I just pay attention if they're attracting or repelling. If the number naturally comes out to be negative, that means you have opposite charges and they are attracting and pulling towards each other. If the number naturally comes out positive, that means that they're the same sign and that they will be pushing away from each other. All right, so that is how you use Coulomb's law to find force. Let's go ahead and use it a couple different ways and then solve for a problem with 3 particles and also solve for a 2-dimensional problem as well. All right, so I screwed some things around. We solved for the first problem right here and got a force of attraction between these two. That's 0.8 newtons. Now say for example we step up the complexity of the problem a little bit and we throw another particle in there, and this one is positive 1 microcoulomb as well, and we have a separation distance between these two of 0.13 meters. Okay, so 13 centimeters or 0.13 meters. We want everything in meters though, so it's in our proper unit for our formula. Okay, now for this one, nothing too crazy. We're still going to use Coulomb's law in a similar way. We're going to find the electrostatic force. We're going to use our constant 9 times 10 to the 9th as we always do. both of our Q values are 1 times 10 to the negative 6th, which you could call that squared. I'll just kind of write it out again for emphasis, showing the Q1 and Q2, and then now we have a 0.13 separation distance, and keep in mind you always need to square that denominator. All right, so you plug that in into your calculator. This time I get an Fe, an electrostatic force, that equals 0.53 newtons. Okay, now comparing that to my other one, obviously 0.53 is smaller than 0.8, and that's because we have a significant drop off in the charge. The other one was -2, and then this one is 1, so it has half the charge, and the distance is a little bit closer, so that kind of increases a little bit, but does not compensate for its lower Q value. Now with these ones, these two are going to repel each other, so we'll call this, we'll say the positive purple charge, that's going to push this one away, and then this one's going to get pushed back some. So if we're just analyzing the middle particle, what you would do is take this number and add this one to it, because we'll call this one, we'll say this is the green negative particle. That one's going to attract it to the left, and then the purple positive one is going to repel it to the left. So both of the forces that are acting on it are both working in the same direction, so we would add them. If they were both pulling it in opposite directions, we would subtract it. So in that case, then we would have a grand net force of 1.33 newtons to the left. All right, now that's how you would handle a one-dimensional Coulomb's law problem with multiple charges. You see if they attract or repel each other. Again, if they're working together to push or pull a particle in a certain direction, you add them up. If they're pushing and pulling in opposite directions, then you're going to go ahead and subtract them. All right, let's go ahead and step it up a notch, and we'll make this a two-dimensional problem. All right, now from here, let's say, for example, we are still focusing on the +1 microcoulomb charge, and then we have the +1 microcoulomb charge up here. We'll say it's still 0.13 meters, and then we'll say that our negative charge is still over here. At 0.15 meters. Okay, now I took all the same distances and charges to kind of save ourselves a little bit of time. This one is still -2 microcoulombs. Now, normally what you would do is you would put it into Coulomb's law twice, and we already did that. We put it into Coulomb's law twice for this orange value and this purple one, and we added up for 1.33. Okay, those ones combine because they're pushing both directly straight left. So now what we can do is let's pull out this black positive charge over here. Okay, now since we know the answer to this already, we know that the green one is going to be pulling it to the left because it's a force of attraction, and that one is the one that we got the 0.8 newtons for. Okay, and then we know the blue one is repelling it downwards. When you add vectors, though, you have to go tip to tail, so where one vector ends, the next one starts. Okay, so this one is getting pushed down, and that's where we got the 0.53 newtons. Okay, now if we want the net force, all we have to do is use some Pythagorean theorem, and then our resultant vector that closes our right triangle is going to be our answer. So if you do a squared plus b squared equals c squared, we have 0.8 squared plus 0.53 squared equals c squared, so basically square rooting both sides. And then you would end up with an answer of 0.96 newtons. Okay, so the hypotenuse of those two vectors combined is our resultant vector, so 0.96 in this case is our net force. And then since it's on an angle, if you wanted the angle, we'll call this angle right here our theta. We can use an inverse trig function. So if we use inverse of tangent, opposite of this angle over here is our blue side, so 0.53, and then our adjacent side is our green side over here, which is 0.8. And if you take the inverse tangent of that, then our unknown angle comes out to 33.52 degrees. Okay, so that's the angle, 33.52 degrees below the horizontal to the left. Okay, so that sums it up for Coulomb's law. Those are the different variations you might use, just two particles attracting or repelling each other. You might have a bunch of things kind of lined up like this. In that case, what you want to do is add or subtract them based on if their forces are working together or against each other. And then finally, we had our two-dimensional problem where you'll have to do some Coulomb's law problems and then a bit of vector addition as well, and then a little bit of trig to find your angle. As a last little tip, let me show you how to solve for R and Q. Now, if you want to solve for R or Q, basically what you're doing is you're just doing some cross multiplication is the way I think about it, as in you would cross multiply these, the R squared would flip over here, and then your F would drop down there, and then you would just square root both sides. So if you want to find your R value, it's basically the square root of KQ1, Q2 divided by the force. Now, if you want to solve for the Q, same kind of method here. I kind of think of it as cross multiplication. So say, for example, you want to solve for Q2. I would do a bit of cross multiplying again, flip the R squared up here, and then take these two and then cross it over here. So then F times R squared over K times Q1 equals Q2. So anytime you're solving something within the formula that's not just solving for force, I kind of just look at it as a bit of cross multiplication and then doing the algebra from there. So I hope that was helpful to you in learning about charges and Coulomb's law. Thank you for watching.